Lecture 18, Deadlock Avoidance. In examining deadlock as a topic, we've introduced the informal definition. We've replaced that with a better, more formal definition. And when we discussed the formal definition, we covered the idea of deadlock's constituent elements. That is to say that there are 4 things that make up deadlock, and they are, if you don't recall, mutual exclusion, hold and wait, no preemption, and a cycle in the resource allocation graph. Now, other than ignore it, which admittedly was worth talking about, even if just for a minute, what about the other thing we've tried so far? We tried deadlock prevention. Now, in prevention, we're attempting to ensure that deadlock never happens by ruling it out categorically. That is, we eliminate one of the conditions that makes deadlock possible, and if we know that that's not the case, if any one of those is absent because we have successfully eliminated it, then okay, we're certain that there is no risk of a deadlock. Unfortunately, as we saw, eliminating each of those 3 things was not a certainty. We could sometimes get away with eliminating mutual exclusion by copying data so things wouldn't be necessary. We could sometimes get away removing hold and wait by using try-lock behavior, but not every resource is suitable for that, and the same is really true of preemption, even if we had the choice. So, all we've really managed to do is make it less likely, and therefore I think we're forced to conclude that we can't live in a world where deadlock is impossible. All we can do is work with a system where it's possible and then try to avoid that occurrence. And this ultimately takes us to the key distinction between deadlock prevention and deadlock avoidance. Prevention is ruling it out for the whole system. Avoidance is we live in a world where deadlock could happen, but we're going to try our hardest to never get in that situation. So just because a deadlock is possible doesn't mean that deadlock is inevitable. That is, we can take some steps to avoid it if we think there is a danger of it actually happening. And we could see there are some strategies that we can use to identify, do we think there is a danger of a deadlock happening? And the goal is to stay out of danger. So, can we do that? Well, the basic strategy for that is do not allow a cycle in the resource allocation graph. And that would prevent the 4th condition from ever being fulfilled, and that would mean a deadlock wouldn't happen. This is something that we might have some control over. We can choose when we're writing a program what resources are requested and the strategy for requesting them and in what order and what have you. So this is something that's really up to us. Some of the things that we needed for deadlock prevention were just not in our hands. You don't control preemption because, that's the operating system's job, and you're just kind of out of luck if the operating system doesn't give you any possibility to do that. We can't make them. In principle, in Linux or something, you could submit a patch which would allow you to turn on this feature given this function call, but good luck getting that one past Linus. However, if you do, hats off to you. Now, the goal to stay out of trouble is, again, keeping in mind a resource allocation graph. You could build one, or you could just sort of imagine what one looks like. You don't necessarily have to draw it or represent it using a graph representation. But we just have to prevent the state of the system being such that if you drew a resource allocation graph of it, it would show a cycle. In the Dining Philosopher's problem, one of the ways that we thought about how could we get around this problem, what could we do that would prevent the philosophers from getting stuck, one of the strategies was hire a bouncer, and if the bouncer prevents any philosophers from sitting at the table, whether it was we limit it to 1 or 2 or 4, even though the table has 5 seats, we said that worked, but I didn't really go into detail as to why. And the correct answer as to why is that with 4 philosophers and 5 chopsticks, there are insufficient requests to form a cycle. right? If we have if we have an image of the dining philosophers sitting at their table, so to speak, then problem occurs when there is a cycle when philosopher 1 is waiting for 2, 2 is waiting for 3, 3 is waiting for 4, 4 is waiting for 5, and 5 is waiting for 1. Now, if we, send one of those philosophers away, so they're not sitting at the table, then philosopher 1 is waiting for 2, 2 is waiting for 3, 3 is waiting for 4, but 4 is not waiting for anybody because there's an empty seat next to them. So then there are insufficient requests, and we don't have a cycle. There is in the resource allocation graph, some arrows that connect all 4 philosophers, but it isn't a cycle the way that it is when there's 5. So sometimes that kind of solution is suitable, that if you know that resources are limited and there's no good way to prevent a scenario where everybody gets some but not enough of what they need, then you can rely on reducing the number of concurrent requests so that resources are distributed, I'll say more unevenly, but it is sufficient. That's good, but I wouldn't call this generalizable to all deadlock situations. There are lots of situations, and you can't always prevent it by saying, well, only this many threads are allowed to run at a time. So, in the words of the legendary Speaker of the UK House of Commons, John Bercow, order, or as he puts it, order. If you didn't watch any of the Brexit debates around 2019 or so, you might not be entirely familiar with this fine fellow, but he has a real commanding voice, and I certainly wish that I sounded like him. But this is what you're stuck with for however many lecture hours of this course remain. Sorry. You'll remember also when we talked about deadlock, we looked at something like this, where we had thread P on the left, where it does wait on A and then wait on B, and then we have a critical section, and then signal or post. Again, they're equivalent. I've managed to stamp out most cases where it said signal, but apparently not here on this thread. And with thread Q, there is a wait on B, a wait on A critical section, and then our signal statements. Okay. Deadlock doesn't take place, I've established, if both threads requested these 2 resources in the same order, and the thing is that it doesn't matter whether we choose A then B, alphabetical order, or B then A, reverse alphabetical order. Some natural ordering might be obvious. There might be a reason why this would work. And don't think that this is hypothetical. I, a couple years back, helped somebody debug a problem that they were having that involved locks, and they would get a deadlock on occasion if they got 2 messages for the same shipment. And why does this happen? Well, the shipment has containers, and it would lock each container and then try to update all of them and everything. And if the containers were in different orders on the 2 messages, you could get a deadlock, because it just replace A with a container number and B with a different container number, and you can see how this goes wrong. And the solution to this, of course, was sort the containers before you try to acquire their respective locks, and it ensures that things always happen in some order. So why does this work? Well, this is, as far as I can recall, the one time there might be like formal mathematical reasoning about this kind of thing in the course. I certainly do not expect you to memorize proofs or anything. You may have had a professor who made you do that, and they might not be your favorite for that or unrelated reasons. But this will just demonstrate why it is the case. So, if the set of all the resources in the system is the set R, which is composed of R0, R1, R2, all the way up to Rm, if we assign to each resource a unique integer value, we have some function f of Ri, it maps a resource to an integer value. This integer value is used for the purposes of comparison, and the rule that you want to enforce is that if a process has been assigned a particular resource Ri, you can request a resource with a different number only if the other resources, the new one's number, is bigger than the one that you currently have. It is important to note that's a strictly greater than relationship, not that that's really a concern in practice. And in theory, if you need more than one of the same resource, you have to request all of those at the same time. So if you're requesting memory or something, you request it in a big chunk and not one byte at a time. Fine. Not super relevant, but in there for completeness. And if you want a resource with a lower number than ones you're currently holding on to, then you have to release any resources so that you're not holding any resources with higher numbers than the one that you want. And if you follow those rules, the circular weight condition cannot hold. And there is a proof of this, and it's a proof by contradiction kind of thing. If you want to think about that between now and when we get there, by all means, it's not too difficult as mathematical proofs go. But again, it's not a key objective of this course that you learn how to prove this. If your intention is to simply take my word for it, I will not object. But yeah, the idea is that we assign numbers to resources, and then resources have to be acquired in the order that corresponds to that number, and this guarantees that we get a consistent ordering. Now, a consistent ordering is fine, any consistent ordering, so the function by which we assign integers is not super important as long as it assigns unique integers to different resources. No big deal. We'll find out when we get to analyzing for lock ordering problems, which admittedly is still a few lectures ahead, how Helgrind, one of the tools of the Valgrind suite, actually does this, and we'll find that it will look for lock ordering problems by assigning an integer value to locks and seeing if you acquire them in the right order, and it has a way of determining what is the right order. That's another one if you want to think about it. Yes, I suppose you could skip ahead to that video and see if someone kindly left you a comment that tells you the answer, but I would prefer that you think about it, how you would assign those integers to resources. So here's the proof. And like I said, it is a proof by contradiction. So we will assume that a circular weight is present, and we'll declare that we have a set of processes, P0 to Pn, could be any of those, and resources are R0 to Rn, again, arbitrarily many of those, and we have a cycle that's formed as process Pi awaits for resource Ri, and that resource is currently assigned to process I plus 1. The exception is, of course, the last one in the chain, Pn, which waits for resource Rn that is held by process P0. And so, since process Pi plus 1 holds resource Ri while requesting Ri plus 1, it means that the integer value assigned to resource I is less than the resource assigned to Ri plus 1. But that means that the integer value for R0 is less than 1, which is less than that of resource 2, 3, and so on all the way up to n, but also less than R0, otherwise the request would not be allowed. And it can't be the case that the integer value for R0 is less than itself. That goes back to just sort of basic mathematical inequalities. When you learned about the greater than and equal sign, and the alligator eats the bigger number or something, this doesn't work. So it's a contradiction, and that demonstrates, in fact, that we could not possibly have a circular weight. So like I said, I think that is the only mathematical proof in the course, and again, please don't memorize it. Okay, but if I asked you, how do you apply this to the dining philosopher's problem, what would you say? And I'll give you a minute to think about that before we go and reveal the answer. Okay, so one of the things, of course, is that we tell the philosophers that they have to pick up chopsticks, in some order. That requires that we devise some sort of order for them to work with. So, what do? Well, I mean, it's reasonably straightforward. You just assign every chopstick a number. You can just draw it on in permanent marker for all that it matters, as long as there is a number associated with every chopstick. And then we tell the philosophers that they are required to request the chopsticks that they want, or try to acquire the chopsticks that they want in ascending order, that is from smaller numbers up to the largest number. So we'll assume that philosophers are agreeable to this behavior, and they don't ask too many questions about why. But the first philosopher will request 0, which is on her left, and then 1 on her right. The second philosopher requests chopstick 1, and then chopstick 2, and so on and so on. And this continues until the last philosopher, who under the previous scenario would have always chosen the chopstick on their left first, which would have been chopstick 4, and then the one on their right, which would have been chopstick 0. But under the new rules, that's forbidden. So this philosopher must request then 0 on his right, and then 4 on his left, because it has rules. And these rules must be followed. So the last philosopher will be blocked when trying to acquire chopstick 0, and it means that chopstick 4 is available for the second to last philosopher, and thus deadlock is avoided. And you can run through all kinds of scenarios about this and sort of try to work out what's actually going to happen. But ultimately, whatever happens with Chopstick Acquisition, everybody will have either 1, 0, or 2. And if you are the philosopher with 2, you can put your chopsticks down, and then they become available for others, and therefore other people will be able to eat. But you can't have the situation where everybody ends up with exactly 1. Imagine, if you will, that philosopher 1 and philosopher 5 are fighting over chopstick 0. They both want the same one. For philosopher 1, it's on their left, and for philosopher 5, it's on their right. One of them will win. If it is philosopher 1, they might pick up the left chopstick, fail to pick up the other one, but in that case, philosopher 5 is blocked and will not try to get chopstick 4 because he's waiting for chopstick 0. That means that chopstick 4 is available for philosopher 4, who can get it, who can eat, and problem is solved, day is saved. Alternatively, if the last philosopher gets chopstick 0, it means that they have one of them, and philosopher 1 has none. And again, they will get blocked. They were trying to get chopstick 0, and in fact, once you demonstrate that in this scenario there is a philosopher that has none, we're actually already done. The rest follows immediately, and that is, if somebody has 0 chopsticks, and there are remaining 4 philosophers and 5 chopsticks, the pigeonhole principle tells you that somebody has 2. So if you wanted to run all possibilities, all you really have to do is prove that in any case, when 2 philosophers fight over a chopstick, one of them gets it. Whichever one loses that race will have 0 chopsticks and will be stuck with 0 for the moment, in which case, of the remaining chopsticks, there are 5, 4 if you count one that's already assigned to somebody, and there are 4 philosophers, and so when you hand out the chopsticks by the pigeonhole principle, then somebody will have 2 of them, they will eat, they will free up the resources. I believe the correct mathematical term for this is you would say, without loss of generality, you would name then a couple of philosophers, and the point is it doesn't matter if it's philosophers 1 and 2, or 2 and 3, or 3 and 4. Not really important. So spin the table around, change the labels, it's all the same. So yeah, that would work. So yeah, we've demonstrated that actually if we apply ordering of resources and it is strictly enforced, then the philosophers will not starve. This also shows why inviting a left-handed person works, because the left-handed person, in this case, does things in the opposite order. They're the person who has chopstick 4 and 0, so they have to request them in a different order than the other philosophers would. Now, in development, ordering is enforced by coding convention and code review, generally. There's no, that I know of, like operating system mechanism that would require you to acquire resources in the correct order. It can be detected at runtime if you did it wrong. That's a thing. But you need to generally make sure that everybody does what they are supposed to do. So if mutexes are acquired in alphabetical order, or their order in some file or something like that, If everybody can follow that, there's no issue, but sometimes it's not as simple because one mutex can be referenced in two pointers, and I said previously, names aren't always consistent because you can have the sender account and the receiver account, and they each have their own mutex called lock, and which is correct, because this time it could be the sender is account A and the receiver is account B, but also concurrently there is also a transaction the sender is B and the recipient is A, so it gets complicated. We will have to think about how to acquire them in the correct order. Stay alert and stay safe. Okay, we're going to take a couple of minutes to watch an excerpt of a video of a couple of anthropomorphic rabbits, which, is peak 90s, trying to cash in on popularity at that time of Looney Tunes and Tiny Toons and what have you. But, hey, why shouldn't you take life lessons from free VHS tapes handed out at Canadian Tire? So, let's watch this, and then we will return.
They both come here to say, to take charge of every day. Stay alert.
Hi, I'm Gert, and this is my brother Bert.
Hi, we're here to help you stay alert and stay safe.
Yeah, so follow along.
Watch out, beware. Things aren't always as they seem. We'll show you what to need. Keep your radar working. Stay alert. Stay safe.
Things aren't always as they appear.
And that goes for people, too. Some people that seem nice at first may be real bad news.
So it's cool to keep your radar working and listen to your instincts.
Yeah, our motto is stay alert and stay safe.
Wonder what's up. Could be trouble.
Hey there, Sonny. How do you get to Albany Avenue?
What should you do if someone stops to talk or ask directions?
Most strangers are nice people,
But some strangers want to hurt kids.
so you've always got to be on your toes.
Let's see how Daniel handles it.
So what do you say, Sonny?
2 blocks that way and turn right. Can't miss it.
Well, would you show me the way?
Sorry, I've got to get home.
Oh, I can drive you.
Sorry.
Way to be, Daniel. Give me 5.
Hi, Gert. Hi, Bert.
You handled that just right.
Yeah, if a stranger stops to talk, always keep your distance.
And never, ever go anywhere with a stranger. Got it?
Whoa! Radar working. Stay alert. Stay safe.
So first of all, let me apologize for the terrible video quality. This is what I managed to find. I don't think it would get that much better if I tried to pull it from a VHS tape. If I could find one and a VHS player and the adapter I would need at the moment to digitize it. So, all right. Important takeaways. Don't get in cars with strangers. Great. What would these rabbits think of Uber or Lyft now that I think about it? Anyway, point being, if you take the lesson away from this of assume the worst case scenario, then the video has served its purpose. Now, is the guy in the car a murderer? I don't know. I didn't see him commit any murders. I mean, certainly his behavior was suspicious, but I didn't see him commit any murders, and we don't know for sure that he is a murderer. And in fact, most people are not murderers, so that's fine. You wouldn't take the chance, though. So we're going to assume the worst case scenario is what's going to happen. And yeah, we're always going to assume that there is a murderer in the vehicle, and if we're wrong, we were perhaps overly cautious, but we're not dead. If we are correct, then, of course, we've made the right decision. Okay. So here's our strategy. Instead of ordering resources, actually the process that wants to run has to give the operating system information about what resources it might want. So processes need to say in advance of execution what is the maximum number of resources of each type that they might conceivably need. In a tape drive system, it's used for backups or something, there's a tape drive, there's a printer, and process A needs the tape drive first to read some data, then the printer to print it out, and another process B uses it in the opposite order, needs the printer and then the tape drive, and knowing this, the operating system could then make more intelligent decisions about what processes should get run when, or when they should be made to wait so that a deadlock does not occur. Now, to understand how the system would look at a particular state of the world, there is a definition that we need to cover, which is a safe state. Now, a safe state is one in which there is some scheduling order. Any one. It doesn't have to be the one that's actually taken, but there has to be a way out. There has to be a scheduling order in which every process can run to completion. Even if all processes suddenly request their maximum resources immediately. And that is part of the worst case scenario planning that we want to consider in this case. So, yeah, it can't be the case that all processes request their maximum resources and then we all get stuck for the state to be considered safe, and that is there has to be kind of a way out. So that's why we need to know in advance the maximum resources that could be required by this process. And more formally, a state is safe if there exists a safe sequence. A safe sequence is a sequence of processes, P1, P2, Pn, and so on, given the current state of allocations. If for each process, P1, that resource requests that it can still make can be satisfied with the currently available resources held, plus resources held by other processes that terminated already ahead of the order. It will make more sense when we actually do an example of how we do this, but basically if we look at the state of the world right now, we'll see, is there any process that can run to completion? If there is, then we'll say, yeah, pretend it runs to completion and releases its resources. When it does that, they're added to the pool, and then we can say, are there any other processes that could now complete? And if we do that, we would say, well, if they ran in the order of, let's say, process C, then D, then J, then A, that would work. You would say that is a safe sequence. Those are all of the processes that are alive right now, and there is a way for them all to finish. So a safe sequence in that case would be the order in which those processes would run and would run to completion. Now, in reality, they don't necessarily run like that, and probably they don't run one at a time the way we are describing, but we just need to know if it's possible. Right, if we are, for whatever reason, not able to prove that the state is safe, that is to say our resource requests can't be granted, based on what we know right now, if everybody requests their maximum resources all at once, then we would say the state is unsafe, and that is, of course, the default. So the magic in it is about the determination of whether a state is safe or not tells us something about deadlock. If the system is in a safe state, it means that there could not possibly be a deadlock. Being in an unsafe state does not mean that there is one, but it means a deadlock is possible because, again, we do the worst case scenario analysis, and you can think of it as, in the best case scenario, of course, nothing goes wrong, you don't get a deadlock, but if the state is unsafe and the worst case scenario happens, then a deadlock could occur. And so if you want to make sure that a deadlock is never going to happen, what you have to do is consider the worst case and, as the topic goes, avoid getting into trouble. Okay, Like I said, I think this makes a lot more sense if we actually look at a specific example. So let's try that. Assume for the moment there's only one kind of resource and it has 10 instances. This is a simple example to get us comfortable with the idea, and not a super good representation of reality, but let's start here and move forward. So there's 10 resources total. There's 3 processes in this system, A, B, and C. A has 3 resources, and at the most it could need 9. B has 2 resources, and it may request up to 4. C currently has 2, and it may request up to 7. And there are, at the moment, 3 resources currently free because of the 10 that exist. 7 of them are presently assigned. Okay, so we have a visual representation of the state shown here at the bottom. So is this state safe? And again, you can take a look at it and sort of analyze it and tell me what you think. I remind you that the assumption is that processes will want to request their maximum resources immediately, and there has to exist a safe sequence, that is an order in which we run processes A, B, and C, assuming that when we start to run a process, its resource allocation goes immediately to max. Okay. So is the state safe? Yes, the state is in fact safe. There exists a safe sequence, and you'll see how we actually get there. So for a state to be safe, you need one path that allows all processes to complete. You could have more than one solution, and if you assign resources to the wrong process, then you don't get the outcome that you're looking for. In this case, because if we look at our initial state, which is shown as A in the sequence diagram here at the left, then we would look at the processes that exist, A, B, and C, the ones that aren't finished yet, and we'll say, well, we have 3 resources. Which process can we give them to? And if we give the 3 resources to process A, then it goes to 6 of 9, so it doesn't have what it needs. B still has 2 of 4, C has 2 of 7, and we get stuck. So obviously if we do that, we've gone in the wrong direction. That would be a path that would lead us to deadlock, but we wouldn't consider that. We wouldn't try it because we know that's wrong. And so looking at the difference between what it has and the max, which of these 3 processes has resource requests that we can satisfy? Obviously, the answer to that is B. It's the only one. So what we would do is assign the resources to B. And so B would get 4 out of 4, and then free resources would be 1. And then we could assume that B runs to completion, so it takes as long as it needs, but it runs to completion, and when it's done, it releases all of its resources, and so that shows us the state labeled C. B got 4 out of 4 in the previous state, it ran to completion, released all its resources, so B now has A, and the free pool has 5. Now, when you're writing this kind of thing, if you were writing it on paper, or if I was drawing it on a whiteboard or a chalkboard or something, I might skip intermediate state B once we're familiar with the concept, because it's not adding much and requires me to reproduce a lot of stuff. I would just say give resources to B and then jump straight to the diagram labeled C. But, of course, since this is the first time we are addressing this concept, showing the intermediate state might make it clearer how we get from one to the other. Then we repeat the process. So we know in our safe sequence, the first step, at least our candidate safe sequence, is B. And then the question is, what do? Do we assign resources to A or C? Slam dunk decision, we assign the resources to C, it gets 7 out of 7, and can run to completion, and then we can see that the 7 resources are available, which is sufficient for A. you'll notice that the last step isn't shown. Actually, the last two steps aren't shown, where A gets 9 out of 9, and then we get shown A with 0 and everything with zeros, because we're finished already. We have developed a safe sequence, and it is B, then C, then A. And moreover, actually, once you're down to exactly one process left in the table, you know you're finished, because deadlock would require 2 or more processes to be stuck. So if you get it down to 1, you're finished. Whichever one is last is the last in the sequence. So that's good. So yeah, this diagram demonstrates that our state is safe, because there exists a safe sequence, B, then C, then A, that allows us to continue even if every process actually requests its maximum resources immediately. Okay, now let's consider a different example. So suppose that A requests a resource and it gets it. So in this case, our initial condition has changed such that A has 4 resources and there are 2 free resources. So in the diagram below, the state changes from A to B. The only difference, again, is shown in the line with A, where A is now 4 in the assigned column, and free is now down to 2. And I repeat the analysis. Is this a safe state? I'll let you consider that for a moment. Okay, I mean, we would execute the same procedure that we did for the previous state. And what does that look like? Well, as Ralph put it, I'm in danger. This state is unsafe. Now, as I said, this does not mean that that necessarily a deadlock will occur. It does not mean a deadlock has occurred. It does not mean a deadlock is certain to occur in the future. It just means this is an unsafe state, and a deadlock could happen in the worst case scenario. Okay, but why? Well, I'll walk you through the solution if you haven't solved it previously, which is that if we look with the 2 free resources, we can assign those to B. B can run to completion, and then the free pool of resources becomes 4. 4 is not sufficient for C, which would need 5, and it's not sufficient for A, which would also need 5, and we therefore have a problem. So we can't give the resources to either A or C and have that work, and therefore we would say the state is not safe because there is no safe sequence. Right. Right. So, yeah. This is worst case scenario, and it is a way of analyzing our situation. There's another approach that we could take to analyzing the situation, one that isn't based on the grid and the table and all of that, which is based directly on the resource allocation graph. So the core idea is, could we use the resource allocation graph to avoid deadlock? Maybe. So an operating system will typically maintain this resource allocation graph. The kind that we want to talk about works if there's one instance of each resource, and it still requires that all resources are declared in advance. But okay, we can live with that unless our operating system is weird and it doesn't let you have resources, but I wouldn't worry about that. And what we have to do is enhance our concept of the resource allocation graph a little bit. The previous version that we had had 2 kinds of edges. There was a request edge and there was an assignment edge, or allocation edge, however you wanted to call that. And so when a process requests a resource but it doesn't get it, that is a request edge. When a process is currently in possession of that resource, it has an assignment edge, and those both work. They get the job done. To make this happen for our deadlock avoidance, we need a third kind of edge in the graph, and it's called a claim edge. And it's a way of indicating that a process might request a resource at some time, and it is drawn with a dashed line. So the dashed lines will appear at the beginning of time when the process might want this resource. If a request actually occurs, then a claim edge is turned into a request edge, so a dotted line becomes solid. If the resource is granted, then it is actually assigned, so the claim edge is replaced in that case with the assignment edge. And upon release, the assignment edge goes back to a claim edge, indicating that a process might want that thing again sometime in the future. So here's a resource allocation graph that shows all three kinds of edge. There's two processes, P1 and P2. P1 is currently assigned to, R1 is currently assigned to P1. It is currently requested by P2, and there exist claim edges here from P1 to R2 and from P2 to R2. So looking at this graph, is there a cycle? No. All right, we can see that there's not that many edges. This is not rocket science. So a resource request doesn't change the direction of any of the arrows. So if P1 requests R2, it doesn't change the direction of the line between P1 and P2, or of the edge, I should say, to be more formally correct. It just makes it solid as opposed to dashed. Now, if there is assignment, if the resource R2 is assigned to P1, then that does change the direction of the edge. And so, basically, what would have to happen to use the resource allocation graph to prevent avoid a deadlock, is that a request is only granted if converting the request to an assignment does not result in a cycle. So if you do a sort of what-if kind of calculation and you say, well, what if I grant this request, and if I grant the request, it ends up making the graph have a cycle, then you would say, no, I'm not going to do that assignment right now. We're going to leave it as an open request until it's safe to do that. So what edge would have to change in this diagram to make a cycle possible? All right, so if R2 is assigned to P2, then we would have a cycle in the graph, counting claim edges, because they do count, and that means a deadlock could happen. It hasn't happened yet because P1 has not requested R2. The dashed line just means hypothetically it could. Now, if it did, that would actually result in a deadlock because P1 would be waiting for P2 and P2 would be waiting for P1 indirectly via those resources. But that might not happen. R2 might be assigned to P2 and P1 doesn't actually ever want resource 2, in which case there's no problem. The deadlock did not occur even though we were in some danger. So, yeah, the key decision is, do we grant a resource? As previously mentioned, this only works if all resource requests are known in advance, and we have to have some idea about how many instances there are of each resource. Okay, so we've covered a couple of approaches, and what I want to talk about now is the banker's algorithm. The banker's algorithm is intended to be more general. It is supposed to work for resources with multiple instances. So the previous analysis for safe state versus unsafe state is in fact the foundation of the banker's algorithm. I would be understanding if you said, oh, I thought the banker's algorithm was, just do whatever makes you rich, and when you run out of money, the government will bail you out. That's not the algorithm that we're studying here. That one is more, psychology or sociology, I suppose, than anything else. But why is it called the banker's algorithm? Okay, yeah, so the banker's algorithm is hypothetically some sort of algorithm that a small-town banker might follow. I don't know how true that actually is. That might be just like how people who write computer textbooks think that bankers behave. But the banker in this case is trying to prevent allocation of cash on hand in such a way that it's not possible to satisfy customers. Thing is that banks lend out more money than they have on hand on the usually correct theory that not everyone will come asking for all their deposits all at once. In fact, if everybody does, not to digress too much on the discussion of banking, but if everybody does ask for their money all at the same time, that's called a run on the bank and is generally considered a disaster. It usually indicates that people have lost faith in the bank as an institution in which to keep their money, and usually central banks step in to send more money to the banks afflicted so that people don't lose confidence in the idea that they will ever get their money back. Now, my mother's stepfather tells a great story, or I should say told a great story, as he's been deceased for a while, but told a great story about how in the 1920s he had managed to save up at the time about $100 in 1929, which, according to online inflation calculator, is something like $1,500 in 2020 dollars. So, a quite significant sum of money for a young person to have saved up. And he kept his money in an institution called the Bank of the United States. Surely, you could imagine, there is no more solid institution than the Bank of the United States. In fact, you probably think it's presently called Bank of America. It is not. The Bank of the United States went under, and in the bankruptcy settlement, in exchange for the deposit money of about $100 that he put in there, he received a settlement check in the amount of 14 cents, which for those keeping score at home is $2.11 in 2020 money. Yeah. Banks. The more courses you take with me and the more examples you hear where I talk about banks, you might come to think that I don't like them. You wouldn't be wrong. In any case, the banker's algorithm is supposed to be about allocating your resources in a fashion that tries to keep you out of trouble. So with my long digression about stock market crashes and what have you behind us, let's actually look at the banker's algorithm. Now, the analysis we did before the resource allocation graph one is the idea of whether the state is safe or unsafe, and the banker's algorithm should be executed when you are going to grant, or when you're considering if you grant a resource allocation, and we want to know, ultimately, does it move the state from safe to unsafe? So you do a what-if calculation. You say, okay, if the request is granted, the new state of the system is this, and make a determination, is the state unsafe? If it is, don't grant the request. Simple enough. If doing this would put us in danger, don't do it. I mean, I can't explain it any more simply than that. Okay. So if the request would put us in danger, then the request will be denied, or the thread or process that wants the resource will be blocked until such time as the request can be fulfilled without putting the system in an unsafe state. And as long as we stick to that rule, then deadlock will be avoided. So the banker's algorithm, as I said, accommodates multiple resources. The textbook that this diagram is from dates back quite a while. So it's full of archaic things like tape drives and plotters and printers and CD-ROMs, and here, the laptop probably has none of those. And why would you print things anyway? You're just killing trees. But okay, fine. Now, the thing is that the previous version of this, where it was just one kind of resource, it was easy enough to represent it two-dimensionally. Now it's gotten a bit harder because, well, you'd have to represent it three-dimensionally, and I'm not really that good at art. So what we have is a couple of tables instead, because this makes it a bit easier to understand. So the left table, or matrix, shows you these are the resources that are currently assigned to each process. So A has 3 tape drives, 0 plotters, 1 printer, 1 CD-ROM. Sure. You can name the resources anything you want. These are ridiculous, but that makes it more fun. And the resources that process A could request, as well as those for each other process, are shown in the table on the right. So A could request 1 additional tape drive, 1 plotter, no more printers, no more CD-ROMs. And then on the right of the second table, there are 3 vectors, and they are existing and what is presently assigned, so it's assigned to processes, and then A is for available. So E is existing, P is for processes have, and A is for available. Nothing to do with any environmental protection agency or anything like that. So E just tells us what are the total resources in the system. So there are 6 tape drives and 3 plotters and 4 printers and 2 CD-ROMs, because this is the strangest computer in the universe. That's fine. Currently, 5 of the tape drives are assigned, 3 plotters, 2 printers, 2 CD-ROMs, and there is 1 tape drive available, no plotters, 2 printers, and 0 CD-ROMs. And obviously, for a given column, P plus A should equal E, which means that the resources in question, they have to be somewhere. Either they're assigned or they're available. They can't be anywhere else. Okay, so our approach for checking how a state is safe works, well, just how you would expect, given our previous discussion of safe and unsafe states. So, given what we have here, given the available resources and the outstanding requests, well, here's the algorithm. Look for a row in the matrix R where the unmet resource needs are less than or equal to the resources available in A. If such a row cannot be found, it means the state is unsafe and we can terminate the algorithm. Assume, as before, the process gets all the resources it needs, mark it as terminated, and put all of its resources into the available pool. Repeat those steps until either we've got it down to all processes have finished, or we are stuck. There's a note on here about choosing more than one process. We'll come back to it after we look at executing the example. Executing it is pretty straightforward, so it's probably silly for me to hold your hand and run through every step in painful detail. But basically, we'll look at the available vector and we'll look at the resources still needed column. And, can we, with the available resources, give everything that A wants? No. What about B? Also, no. What about C? Still no. What about D? Yes. What about E? No. Because for A, B, C, and E, we can eliminate it immediately because there's no plotters available. So what do? Well, we give the resources to D because the available vectors contains what it needs. There's 2 printers and it only needs 1 printer. So we would say yes, that is complete. We could then cross D out of the list. And then we would say, okay, the available resources is now the A vector plus what we just got back from D, and you can subtract it from the P vector as well. And so D has 1 tape drive, 1 plotter, and 1 CD-ROM, so we would add that to the available pool, meaning there are 2 tape drives, 1 plotter, 2 printers, and 1 CD-ROM now available. So 2, 1, 2, 1 is our new A vector. Can we meet the needs of any process at this point which requests those things? Yes, we can. We could pick E. That would work. You could also pick A. And this is what I mean about it doesn't matter all that much. It actually can never make your situation worse. So what do I mean by it can never make your situation worse? So if I choose process A, then it doesn't eliminate E. Because when A runs to completion and it finishes, it releases some resources. In the worst case scenario, it's actually like process E where there are no resources available. So if we run E right now and it releases all its resources, we're no worse off. If we run A, it has some resources, so the pool of resources will increase. So if ever you have 2 options, or more than 2 options, for this is a process I could run with the available resources, there's no wrong choice. You could choose either one of them, and it doesn't affect your ability. You won't get stuck. So you can still run to completion. So we could do D, then E, then A, or D, then A, then E, and it will be fine because the pool of available resources can't shrink as a result of this process. So if we add the resources from A to the newly available pool, we will see, how are we doing in terms of the allocated resources. Well, now we've increased the available tape drives to 5, and plotters is still at 1, and printers has increased, actually it's not increased, sorry, it's increased by 1, so printers is now at 3, and CD-ROMs is also increased by 1. So it is at 2. And we can apply this vector over and over and over again until we have made a determination of a safe sequence. And as I say, there could be more than one. We've already encountered that once we have chosen D and it releases resources, our next choice could be either E or A. And that means there exists more than one safe sequence, and any one that you give as your answer is fine. And that's what I mean with the last couple of notes here on this slide that says, look, more than one process can be chosen in this step. It doesn't matter at all which one, because the pool of resources can't get smaller. So ultimately what we'll do is, as previously mentioned, a what-if calculation. That when a resource is requested, we will think carefully about, well, if I grant this resource, what happens? And so if we go back to the banker's algorithm type thing, if we had an incoming request from process E to get one printer, okay, then you would apply that change as in the what if calculation. So you would alter the matrix on the left such that E is 0, 0, 1, 0. In its resources assigned, and you would update the P and A vectors accordingly. And then you would say, okay, if I do that, is the state still safe? Is the state still safe? I'll let you think about that. You can work it out sort of by the same procedure. And you will make a determination as to if it's safe based on whether or not you find a safe sequence. Okay, you should in fact find that there is a safe sequence, as far as I can tell by just glancing at it casually, because if we assign one of those resources to E, then it reduces the resources that it could still need. So the resources still needed changes to 2100, and we can still run D with the available resources, and then we can run A and we can run E again, so it will all work out just fine. However, we could make another change, which would be an unsafe one, which would mean that that resource request should be denied, or at least delayed. Okay, so here's the bad news. The banker's algorithm is great in theory, but in practice it's utterly useless. Why is it utterly useless? When I introduced it, I went over a couple of notes about, here are preconditions for the banker's algorithm. And they are things like, well, a process needs to know in advance what its maximum resource needs could ever be. That's kind of unrealistic because, we don't know what resources we're going to want, especially in a process that's user interactive. I don't know, the user's going to tell me what they want, and then we'll figure out how to do it. So I don't know what resources I'm going to need. Another thing is that the number of processes is not fixed. It varies with users' wishes. They start processes or they terminate them. Things will happen. Finally, a resource that was thought to be available can suddenly vanish. Unplug a printer, a network goes down, something breaks, what have you. So there's lots of possibility for the resources to suddenly change, and change in a way that's kind of unavoidable. The printer breaks, the printer breaks. Printers are temperamental like that. But if the printer breaks, there's no way you can sort of turn back time and force somehow the state to go back to safe. That could move you unintentionally to an unsafe state. And we haven't even touched on the problem that we don't actually have a good way to defer or deny those resource requests. The operating system would have to do it for us. And basically, they don't. So, yeah, it turns out, in practice, the banker's algorithm can almost never be used. Yeah, that doesn't feel nice. That doesn't feel nice at all. The banker's algorithm has appeared in the past, at least in UC 254, the predecessor course to this, as an exam question, just because it's an algorithm that you can execute, and you can do an analysis of whether a state is safe or unsafe. But yeah, it's kind of useless. So that sucks. So where does that leave us on deadlock avoidance? Ultimately, all of the techniques that we've looked at, whether it was just a simple, safe, unsafe state determination, whether it was the banker's algorithm, whether it is the resource allocation graph, depend on us knowing things that in practice it's not possible really to know. Right? We don't know what resources are going to be requested by what processes in advance. Even if we wrote the process, there's all kinds of ways that we could be uncertain. And it also requires that the number of resources in the system is fixed and never changes, and that we know is also not true unless we are talking about some sort of embedded system. This is the Mars rover, and all the equipment it comes with is all the equipment it will ever have, because it's rather inconvenient to install new equipment on things that are currently on another planet. Same thing for a satellite. It's a bit of a pain to just fly up there in outer space and plug in this USB device. So avoidance kind of doesn't work. There are some steps we can take when it comes to avoidance to sort of stay out of trouble without too much magic, or without using things that we can't use or knowing things we can't know, but it's not great. The other thing is that because it deals in worst case scenario, even if we can do avoidance, we are reducing system performance in the name of safety. If we limit the number of philosophers at the table to 1, we're reducing the rate at which they can eat in the name of safety, preventing them from getting deadlocked. You might not consider that to be a worthwhile trade. So ultimately, here we are at the end of avoidance. We've talked about prevention, and we said, well, you can't truly prevent it. All you can do is make it less likely, or maybe rule it out in a few edge cases. We've talked about avoidance, and I've said, well, avoidance would be great, and it would be nice if we could do that, but again, only in certain edge cases and only under the right conditions. So where does that leave us? Well, it leaves us with the last option for dealing with deadlock that appeared in our list when the topic was introduced, and that is deadlock detection. And it is with resignation that we talk about deadlock detection as our next topic, which is if we can't stop it, then the next best thing that we could do is notice when it happens, because if we do, then we could have an opportunity to do something about it. But that I will save for the next video, so I will see you then.